We ask AI to write our emails, to create incredible art, and even to help us drive our cars. But have you ever really stopped to wonder, how does it actually think? Today, we're going to try and crack open that black box. We're looking at some fascinating new research that's trying to figure out not just what an AI does, but how it's doing it. All right, think about this for a second. You're writing some code, maybe Python. You type print, an open parentheses, and an open quote, and almost like magic, the AI auto-completes, knowing that you're eventually going to need a closing quote. How? What's the thought process there? What's going on inside its head?
Well, here's the wild part. For many of the most powerful AIs we use every day, the honest-to-goodness answer is, we don't really know. They're a black box. We see the input, we see the output, but the logic in the middle is a complete mystery. And a huge reason for this comes down to one tricky concept.
And that concept is superposition. Seriously, imagine trying to follow a single thread of yarn in a giant, hopelessly tangled knot. That's what it's like trying to find a single concept like, is a quote open, inside a normal AI. The idea is just smeared all over the place, across thousands of connections, making it practically impossible to trace.
So this is the central challenge for AI safety. And, well, just understanding what we've built, how do we unravel this magic trick to see the actual mechanics behind it all?
To tackle this, some researchers tried something completely different, kind of radical actually. They figured, instead of trying to untangle this messy ball of yarn, what if we built an AI that wasn't allowed to get tangled in the first place?
And this slide right here perfectly captures the two different approaches. On one side, you've got your standard dense models. They're incredibly powerful, but they're a total black box. And then you have this new idea, weight-sparse models. They're designed from the ground up to be simpler and way more transparent, trading some of that raw power for something we can actually read, a blueprint.
So how'd they actually build this transparent AI? It was a pretty cool process. They started with a standard model, but then they did something wild. They forced nearly all of its connections, like 99.9% of them, to just switch off, go to zero. Then they trained this new, super sparse model on a bunch of Python code. And finally, for any specific task, they'd prune it down even more to find the absolute bare-bones circuit it needed to get the job done.
And this is where it gets really, really exciting. By doing all of this, they were able to literally reverse engineer the AI's thought process for specific tasks, like the one we started with. So, let's go all the way back to our opening mystery. How does the AI know to close a string with the right kind of quote? With this new see-through model, we can actually trace the exact path the information takes, neuron by neuron. It's incredible.
And what they found was, wow, it was just shockingly simple. In one of the first layers, individual neurons had developed these single, very understandable jobs. One neuron basically became a quote detector. Its only job was to fire up whenever it saw any kind of opening quote. Another one became a quote type classifier. It would activate positively for a double quote and negatively for a single quote. I mean, it's just that clean. Then, a little later in the model, another part acts like a manager. It uses that quote detector signal to say, okay, a string was opened. I need to pay attention. And then it uses the quote type signal to know which specific quote it was. After that, it simply copies that information to the end of the string to predict the right closing quote. It's a clear two-step algorithm that you or I could actually follow on a whiteboard. The researchers themselves were pretty blown away. They wrote that this work produces circuits that achieve an unprecedented level of human understandability. And that's not just academic hype. Being able to point to individual neurons and describe their jobs in plain English is a huge, huge leap forward for this field. But, and you knew there was going to be a but, right? This incredible clarity, this new understanding, it doesn't come for free. It has a very specific set of costs and consequences.
You see, the crucial point is, once you have the blueprint for how a machine thinks, you also have the blueprint for how to trick it. Understanding the logic makes the model predictable, and because it's predictable, it's also vulnerable.
For instance, the researchers figured out the circuit for counting nested brackets. Turns out the model does it by basically averaging an open bracket signal over the whole piece of code. So the attack is simple. Just add a bunch of distractor brackets inside a code comment. The model sees them, gets confused, its average gets thrown off, and it fails to close the list correctly. They call this context delusion.
So these models are easier to trick, for sure. But that's not the only limitation. This whole method of building understandable AIs has a much more fundamental, much bigger trade-off.
And this is the core trade-off, right here. As this chart shows, as you crank up the interpretability,
By making the model sparser and simpler, you generally have to crank down its overall capability and performance. For now, it seems the two are inversely related.
Now, the upside is incredible. These weight-sparse models learn circuits that are, on average, 16 times smaller and simpler than the circuits you'd find inside a normal, dense model. That is a massive win for clarity.
But the downside is just as massive. To get that amazing clarity, these sparse models require a staggering 100 to 1,000 times more computing power to train. They are just incredibly, wildly inefficient.
So, if these sparse models are way too inefficient to become the next ChatGPT, what are they even good for? Well, this is where the research gets really clever about the future.
They can be treated as model organisms, like the lab rats or fruit flies of AI research. By studying these simple, understandable models, we can discover fundamental principles about how neural networks learn and compute, principles that probably apply to their bigger, more complex, black box cousins too.
And they're already building on this. The next step is creating these bridges that can map the simple computations from these sparse models onto the messy, complicated inner workings of the dense models. It's like having a Rosetta Stone to finally help us translate the language of the black box.
This research is a huge step forward, no doubt, but it also really sharpens the fundamental challenge we're facing. Can we actually build AI that is both incredibly powerful and completely transparent? Finding the answer to that question is going to define the entire future of artificial intelligence.